These are notes on specific heat, which is Chapter 17, Section 1 in your book. Those of you who have taken physical science or chem lab methods probably talked about specific heat then and maybe even did some labs, so this should be a little bit of review for most of you. We are, however, then going to bring in some calculations that will probably be new to most of you. So specific heat is essentially a measure of thermal inertia. We've all studied Newton's 3 laws, and we know that the first law is the law of inertia. Objects in motion stay in motion, objects at rest stay at rest unless acted on by an outside force. So let's just quickly review inertia before we talk about thermal inertia, because it's a good analogy. So inertia is how easily something accelerates. The higher the mass, the higher the inertia, meaning the more likely it is that that object will keep doing what it's doing or not accelerate. So let's take the example of an elephant. An elephant has a very high mass, so it has a very high inertia. So it's likely to keep doing what it's doing. If the elephant is stopped, it's going to stay stopped. It's going to take a pretty big force to accelerate that elephant, get it to start moving. But if this elephant is charging at you, it's going to take a pretty big force to stop it as well. It's going to be likely to keep charging at you or to keep going, and it's going to take a big force to stop it. Compare that to like a cat. That has a much lower mass, so a lower inertia. It's easy to get a cat to start moving when it's stopped. Similarly, if the cat is running at you, it doesn't take that big a force to get it to stop. So that's inertia when we're talking about forces, and it's the force that changes the object's motion. When we're looking at thermal inertia, or specific heat, we're looking at how easily something changes its temperature, not its motion. And the thing that changes its temperature is energy added or energy removed. When we're talking about energy added or removed to change temperature, we're talking about heat. So that's the difference between heat and temperature. Having a high specific heat means it's more likely to stay the same temperature, not heat up or cool down. Just like inertia, the higher the mass, the higher the inertia, the more likely to keep doing what it's doing. The higher the specific heat, the more likely it is to stay at the same temperature. It's going to take a lot of heat to change the temperature, either up or remove a lot of heat to lower the temperature. Let's look at an example. So let's look at pizza. Let's say we take a pizza out of the oven, maybe a 400 degrees oven. So right when we take it out, it's been sitting in this oven, everything is at thermal equilibrium on this pizza. The crust, the cheese, and the sauce are all at 400 degrees. But we know that we can cut the pizza up into slices, say, and we can take a slice and we can hold it very comfortably in our hand. We can hold the crust in our hand. But then when we take a bite, we burn our mouths because the cheese and sauce are still really hot. All of these started out at the same temperature, but the crust cooled down a lot faster than the cheese and sauce. So the question is, which has the higher specific heat, the crust or the cheese and sauce? Go ahead and pause the video, think about that, come up with an answer. You should have said the cheese and sauce have the higher specific heat because they were more likely to stay at 400 degrees. You need to remove a lot more energy from the sauce and cheese to get their temperature to cool than you need to remove from the crust. The crust cools pretty easily, mostly because there's a lot of air in the crust, and air has a very low specific heat. It heats up quickly, it cools down quickly. It doesn't take a lot of energy to heat up air. Similarly, you don't need to remove a lot of energy to cool down air. That's why we get such big temperature swings between day and night. So what specific heat actually is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. And the unit for that is joules or calories per gram times degree Celsius. And we're going to look at how that breaks down in a minute. Before we do that though, let's look at how joules and calories play out, because the unit is joules or calories. Your book is going to list specific heats in both joules per gram degree Celsius and calories per gram degree Celsius. So to convert between the two, 1 calorie equals 4.18 joules. So let's look at an equation that relates specific heat, the mass of the substance, the temperature change, and the heat required, either needing to be removed or needing to be added. So the equation is Q equals Cm delta T. And I remember this as, and I'm going to break it down for you in a minute, but I remember the equation as Q equals Cmat. Obviously the delta is not an A, but it helps me to remember the equation. Q equals Cm delta T. In the equation, Q equals heat. It's energy that transfers between two objects, heat always transferring from warm objects to cold objects because of a difference in temperature, and that's either going to be measured in joules or calories. The C is the specific heat, which is measured in joules or calories over gram degrees Celsius. The important thing to note is if you're using the specific heat with the calories, then the Q you end up will be in calories. If you're using the specific heat for joules, then the Q needs to be in joules. So you need to make sure that your units are corresponding. The M is the mass of the substance in grams. Obviously, take an example we all know, say water. It's going to take more heat to heat up more water, so the mass of the substance clearly matters. And delta T is the change in temperature. Temperature final minus temperature initial in degrees Celsius. Which means that if you're heating something up, your temperature final minus your temperature initial, your change in temperature is going to be positive. So your Q is going to be positive. An interesting aside, which we'll get to a little later, is that if you're cooling something down, your T initial minus, or your T final minus your T initial will be negative, meaning your Q will be negative. Let's look at an example. How much heat is required to raise 100 milliliters of water from 50 degrees Celsius to 70 degrees Celsius, knowing that the specific heat of water is 4.18 joules per gram degrees Celsius. So pause the video, set this up, and then check your work. You should have had this equation. Q equals 4.18 joules per gram degrees Celsius times 100 grams, remembering that water's density is 1, so 1 gram equals 1 milliliter of water, times 70 degrees Celsius minus 50 degrees Celsius. And what's interesting here is that you can see where the units are going to cancel out. So the grams are going to cancel here. The degrees Celsius cancels here. Obviously, when you do 70 minus 50, you get 20 degrees Celsius. And so you're left with joules, which is the unit you need for your Q. So go ahead and calculate this and then check your answer. And so you should have gotten 8,360 joules. If we're looking at significant figures, we would go with actually we probably should go with one significant figure because we've got the 100. Realistically, I should have made this 3 significant figures, but it doesn't matter. The point being, if you're looking at 2 significant figures for the temperature, oh no, that's 1, 2. All right, so really we should be going with 8,000 joules, not 8,400. I don't like the way I set up this as far as significant figures. There we go, but it's not a big deal. All right, let's take another example. So example 2, how much heat is required to raise 1.00, and let me switch this, I didn't mean times 10 to the third, I meant times 10 to the second. Sorry, all right, now we're fixed. How much heat is required to raise 1.00 times 10 to the second grams of aluminum from 50.0 degrees Celsius to 70.0 degrees Celsius? So essentially the exact same question as before, except that the specific heat of aluminum is 0.900 joules grams degrees Celsius, joules per gram degrees Celsius. So go ahead and set that up. And so you should have something that looks like this, and you'll notice this time I've fixed our significant figure issue, and go ahead and solve this and see what you get. So you should have gotten 1800 joules, or in this case we have three significant figures, 1.80 times 10 to the third joules. So compare these two numbers, 1800 joules with 8000 joules. We've raised the exact same mass of two different substances, the exact same amount. So each of these substances, we had 100 grams of each one, and we raised them both 20 degrees. But it took significantly less energy to raise the aluminum that amount than to raise the water. That's why we say water has a higher specific heat, or that's what it means that water then has the higher specific heat. That it took more energy to raise water the same amount that we raised the aluminum by a lot. I mean, that's almost more than 4 times as much. All right, let's look at one more example. So this example, I'm not going to give you the answer to right now. I'm going to show you how to set it up, but then this is going to be our warm-up question tomorrow. But you need to have already thought of it so that you have some answer that you can give. We're not going to spend 10 minutes so that everybody can sort of figure it out. Obviously, we'll go over it. But I want you to have something figured out before tomorrow. So let's take this example. You have 100 grams of iron and 100 grams of water. You heat the iron to 70 degrees Celsius, and then you put it in the water. And let's say that water was at 30 degrees Celsius to begin with. After a certain time, the copper and water have reached equilibrium. Heat's going to flow from the iron to the water because the iron is warmer. But at some point, they'll be at equilibrium. They'll be at the same temperature. The iron's going to lose temperature and the water's going to gain temperature. What is the equilibrium temperature? So they should both reach the same temperature. What's that temperature going to be? And then what's the delta T for each substance? Which might surprise you. If you're not sure, if you can't get that far, at least think about, will it be the same delta T? Are these going to gain and lose the same amount of temperature? So some things you need: the specific heat for iron is 0.46 joules per gram degrees Celsius, and the specific heat for water is 4.18 joules per gram degrees Celsius. I know I put in one significant figure now that I'm looking at this, but solve it to 2 significant figures from the specific heat of the iron, and pretend like I thought this through more clearly and put in 2 significant figures for all of them. One of the things to get you started is to maybe make a chart with the Q, the C, the M, the T initial, and the T final for both iron and water. Put in what you have and then figure out what you're going to solve for. The other hint is think about what things will be the same. We already know that the final temperature is going to be the same, so that's really one variable, not 2 variables. The temperature final of the iron equals the temperature final of the water, so it might look from the onset that you've got tons and tons of variables. But for the things you don't have, try to figure out which things will be the same. See how far you can get, and this will be our warm-up question tomorrow. Good luck.